Welcome, ladies and gentlemen, to my video course Signal Flow Graphs in 12 Short Lessons. My name is Hans-Peter Schmid. The topic of this first video is equations and signal flow graphs. In this video, I want to show you that an equation system and a signal flow graph are just two different ways to write down exactly the same thing. Now, what is a signal flow graph? A signal flow graph consists of nodes and branches. Nodes are drawn as small circles, and branches are drawn as lines with arrows on them to indicate a direction. The nodes are used to represent variables, x, y, and z in this example, and the branches are used to denote multipliers, here a and b. Addition is simply done by leading several branches into one node. So therefore the signal flow graph, or SFG, you see here represents a simple equation: z equals a times x plus b times y. Once you know this, the rest is quite straightforward. So drawing a signal flow graph, if you have an equation system, is quite simple. I show this to you with a simple equation system with two equations and three variables. The three variables, x, y, and z, we will draw using three nodes. Then the second equation can be drawn with one branch, z equals b times y. The first equation is a sum of two terms and needs two branches, one for the part y equals x and the other one for y equals minus az. Y equals x minus az is the result because the two contributions are added, the two branches both go into the node labeled y. How exactly an SFG looks depends on where we draw the nodes. We can just as simply draw the nodes somewhere else, and the signal flow graph will look quite different, although it encodes exactly the same equations. It is also simple to add equations by just adding branches to our graph. When we do that, the two different versions of our signal flow graph already look quite different, but I can assure you that they describe absolutely the same thing. One big advantage of using signal flow graphs is that you can immediately recognize dependent variables y, z, and w simply because branches go into them, and independent variables x because branches only leave them. Going the opposite way is just as simple. Now I will show you how you can write down an equation system if you have a signal flow graph. I use something bigger this time with 4 nodes and 5 branches. Writing the equation system down is simple if you do it node by node. So let's do that. First node, x, obviously an independent variable, so there's no equation describing it. Y has 2 branches going into it, which gives the equation y equals ax plus ew. Z also has 2 branches going into it, giving by plus dw. Finally, w has 1 branch going into it, and the equation is w equals cz. Signal flow graphs and equation systems, the same thing. Don't forget this simple relationship ever, please. Later you will learn how to draw signal flow graphs from electronic systems directly without even thinking about equations. You will learn lots of rules of thumb, but sometimes you have to do something where you don't have a rule of thumb to do it, and then will be the time when you have to remember that you are actually only drawing equation systems. You can always write down an equation and draw this as a signal flow graph. And most of the failures of students using signal flow graphs later, when it gets more complicated, actually happen because they have forgot the simple correspondence between the graph and the equations. There's the second thing I want to make sure you don't forget. Don't solve it like this. Writing a signal flow graph down as an equation system and then solving that equation system is a very inefficient way to do it. How to solve it without ever looking at the equation system written down is the topic of the second video in this short course. Many of you will have noticed by now that what I'm doing here is very similar to drawing a block diagram. So next, let's look at how exactly signal flow graphs relate to block diagrams. For this I use a simple signal flow graph with 3 nodes and 3 branches. And this expresses the same thing as a block diagram with an amplification mu, a feedback beta, and then an adder that has a negative and a positive input. In this block diagram, the variables are now also written on the lines. So you already see there's much more to draw for the same content if you use a block diagram instead of a signal flow graph. However, there's one very important thing to remember, and this is that the block diagram normally contains equations as well as causality. The amplifier block doesn't just mean z equals mu y, it means z equals mu y because y controls z. You can of course also let a signal flow graph denote causality, but there it is very easy to break. For example, the signal flow graph you see here is just another way to write this equation system with 2 equations. We can simply rearrange the first equation and then use the new equation system to draw a new graph. Now what you see here is exactly the same equation system, but if you now understand it as causal, it implies something completely different. In the old signal flow graph, x was the independent variable, now y is the independent variable. So if you do operations like this on signal flow graphs, then the equations still give exactly the same results, but causality is broken. So this concludes the first of the 12 short videos about signal flow graphs. What have you learned in this video? Signal flow graphs represent equation systems, or to be mathematically precise, linear equation systems. Additionally, you can use them to represent causality, which we will often do in this course. But if the only reason to use signal flow graphs were to draw an equation system graphically, they would actually be quite pointless. It is true that you can see some things in the graph which are harder to see in the equations themselves, but the true benefit from using signal flow graphs comes from the fact that you can solve the equation systems they represent without ever writing the equation systems down, simply by looking at the graph. This is done using Mason's gain rule, which is the topic of video episode 2. Now all you heard here sounds quite simple, and you may be tempted to say it's so simple it will be in my memory forever, but this is not so. Signal flow graphs is not something you learn, it's something you do. And if you really want to be able to do this, then you should now do a few exercises. I recommend that you just write down for yourself equation systems and draw signal flow graphs belonging to those equation systems. Do 6 of them and check them again whether you did it right. Then draw a few signal flow graphs and write down their equation systems going the other directions. Also do 6 of those. Finally, pick the signal flow graph you like best, take its equation system, reorder some of the equations to make a different variable independent, and then draw the signal flow graph again from the new equation system and spend a bit of time to meditate over the big difference you see in those 2 graphs. I'm convinced that if you do this, then you will remember the contents of this lesson for a very long time. Thank you for watching this video number 1, and I hope to have you back again for episode 2 of Signal Flow Graphs in 12 short lessons.